Hey everyone, welcome to class today. Today we're going to be covering evidence for the Big Bang Theory. So we're in our astronomy notes. If you want to follow along, go to Schoology and get into the notes on astronomy. The same ones that we've been using all along, those are the ones that we're going to be using today. Just like normal, I've just added on to the end. So today we're going to be talking about evidence for the Big Bang, and we've already covered numbers 1 through 4. Today we're only going to cover number 5. Number 1, now remember that these are the 6 key pieces of evidence for the Big Bang Theory. There's lots more evidence out there than just these 6, but I've pulled these 6 together as what I think are the 6 most convincing, most important pieces of evidence for the Big Bang Theory. And I'm going to make my little disclaimer that I always make. This is the most scientific, most well supported theory about the beginning of the universe, about the origins of the universe. But like I've said in the past, this isn't the only theory. This isn't the only idea out there. And so this is the one that I have to cover in class. This is what we're going to talk about today. So I'm hoping that you don't get too upset about this, but we're going to talk about the Big Bang Theory today. Okay. Number 1, universal expansion and Hubble's law. We talked about this. This is the most important, in my opinion, is the most important, most convincing piece of evidence for the Big Bang Theory. Universal expansion and Hubble's law tells us that the things in the universe today are expanding universally, and the things that are farther away from us, this is Hubble's law, the things that are farther away from us are actually traveling faster than the things that are closer than us, or closer to us. The reason that this is such good evidence for the Big Bang Theory is that if the things today are farther apart than they were yesterday, and yesterday they were farther apart than the day before, well then we can just keep turning back the time. And if we can turn back the time far enough, we reach a point where everything comes together in one single singularity. And we've done this with simulations. Okay, so this is pretty good evidence for the Big Bang Theory. In my opinion, that's the strongest. Just turning back the clock. Number 2 is the cosmic microwave background, or that background radiation that's left over, that static that's left over from the Big Bang Theory, or from the Big Bang. Okay, this is important evidence for the Big Bang because it's long before we had the ability to measure microwave light, microwave energy, we were able to predict it. Scientists said, hey, if the Big Bang had happened, it should have this leftover static, and it should look something like this. And they put together, some characteristics of what it could look like. And in the early 90s, with the Kobe telescope, when they finally had the technology and ability to measure the cosmic microwave background, not only did they find that it was there, their prediction that it was there was correct, but it also matched their predictions almost exactly. I mean, they were almost indistinguishable. Their findings and what they had predicted, what they thought that they should find, were almost indistinguishable. That's pretty important. That tells me that they are on the right track. So number 1 and number 2 are really the 2 best pieces of evidence for the Big Bang Theory, in my opinion. Number 3, quasars. We talked about these last time. These are super cool. They're really mysterious, big giant lightsabers of death that are galactic size. They're really cool. The reason that these are evidence for the Big Bang is because these only happen at the outer edges of our universe. And remember, as we look out into the outer edges of our universe, as we look away from us, we're actually looking back in time because we see the edge of the universe as the way it was, 13 billion years ago. And quasars only happen in that one specific time range between about 10 billion light years away to about 13 billion light years away. So that tells us that the universe has been changing over time. At one time, the universe had a lot more energy densely packed into one area. Enough energy that was close enough together that it was feeding those active galactic nuclei, those black holes, and that was causing these quasars to form in the center of galaxies. So the universe has been changing over time. While this isn't direct evidence for the Big Bang, the fact that it has been changing and we can see how it's been changing, I think, is important and lends credit to the Big Bang Theory. Number 4, radioactive decay. This is the last one that we covered. If we can measure rocks that are really, really old, well then we know that the universe is really, really old. We've measured rocks that are on Earth, from Earth, at about 4.2 billion years old. Now, that tells us that the Earth is at least 4.2 billion years old. It could be older. In fact, we do believe that it is older. We believe it's 4.6 billion years old, or 4.7, depending on how you round it. But it's got to be at least 4.2 because we're finding rocks that formed here, and we're able to date them. We're able to figure out how old they are. Now, remember, we found an asteroid, or a piece of an asteroid that we found on Earth. It was 7.2 billion years. That actually would have come from somewhere else in the universe. It didn't come from our solar system, which is pretty cool. Just yesterday, I don't know if you guys saw, actually it would have been, for you guys, it would have been 2 days ago, the OSIRIS-REx mission, which you probably have never heard about. 2 years ago, NASA launched a satellite called the OSIRIS-REx, and its goal was to catch up to a small asteroid that came out of the asteroid belt and is no longer orbiting within the asteroid belt, but orbiting the sun on a different path. The asteroid's name is Burma. OSIRIS-REx's goal was to catch up to Burma and land on Burma and collect samples. Well, just a couple days ago, that happened. And if you want to watch the live feed of it happening, I have it posted in the red folder on Schoology, so you can go check it out there. But it happened. We landed on an asteroid, and we collected samples. We, meaning a probe, a robot. They collected samples, and it's now on its way back to Earth. I guarantee you the first thing that they're going to do is they're going to check they're going to use radiometric dating and this idea of radioactive decay to figure out how old it is. Guarantee that'll be the first thing we do. That's the most important. We have to know how old it is before we can really do any sort of studying it in any great detail. All right, and then today we're going to be talking about stellar formation and stellar evolution. Now, I know I'm going to be talking about stars almost as if they're alive. I mean, we're using the word evolution, and I'll be using the word life cycle, and stars are born and stars are dying. And but we all know clearly stars are not alive. I just want to point that out to you guys, okay? All right, so this next slide is the notes that we're taking for today. And I know that normally I make all the text orange. I forgot to do that, and so the text is blue, but I want you to put all of this in your notes today. These 2 bullet points, okay? Number 5, stellar formation and stellar evolution. We observe stars all over the universe, and we can observe them using relatively new tools, telescopes, and now we use satellites, which are really just space-based telescopes, and we use them to view all sorts of stuff in the night sky. But we can, when we look at individual stars, we can see stars. Here's a chart down here of stars in various parts of their life cycle. We can view stars in all of these. Average stars, which we see all the time, red giants, super red giants, nebula, neutron stars, and supernova and black holes are more rare, but we can see them. Okay. So this picture here, I don't know where this picture was actually taken. I stole it off of Google, but this is a telescope. Well, okay, inside of here there's a telescope. This is a big dome, and this dome here can spin. There's some sort of bearings and a motor that turns this whole big top piece. It spins it, and so you can face it in any direction. And these doors open up sort of like the doors at Walmart, and they open up on either side, and they reveal just this little tiny crack here, and inside of there is the telescope, and then you can point it up and down. That's why that slit is there. And we have a few of these telescopes in the Kansas City area. One is at UMKC, has a fairly nice one, so I've been told. I've never been to that one. But there's one even closer. There's one out by Lewisburg called the Powell Observatory. The Powell Observatory is great because they actually open up to the public quite often. You can go there for free. It doesn't cost anything, and you can go out and check it out. It's run by the Astronomical Society of Kansas City, and I'll put a link. I'll put a link on Schoology for that. It's a good organization. You might want to think about joining it if you're really interested in this kind of stuff. Not only does it get you more access to this planetarium, to the gosh, I just blanked on the name of it. Powell Observatory. Thank you. PAL Observatory. It gets you more access to the PAL Observatory, but they also give you access to monthly meetings, and there's you get access to the YCO Observatory in UMKC. And the coolest part is, if you take the classes, they offer free classes. You can actually get your own key to the observatory, and you can have your own key to the PAL Observatory, which is pretty dang cool. You might look into it if you're interested. Okay. So anyway, using tools like this observatory here, like the PAL Observatory and other space-based telescopes, we're able to see all these stars in different life cycles. Okay. Now, I'm about out of time on this video, so what I'm going to do is I'm going to stop this video. So this will be part 1. I'm going to stop this video now, and I'm going to go start my next video, which will be part 2 for the day. So go ahead and go find that in Schoology. It'll be in the purple folder, same place you found this one.